Hello my friends and welcome back to the You Can Do TV channel.
Bent continuously, yet keeping clean edges, steel plates reveal the control of the 3-roll bending machine. The numerically controlled 3-roll variable axis plate bending machine answers that by adjusting force, position, and angle in real time while the plate stays under constant guidance. Material positioning sets everything in motion. The plate is aligned between the 3 rolls, with side supports holding geometry steady before pressure builds. Instead of forcing a fixed path, the machine adapts roll angles to match plate thickness and width. That setup feels like the machine is reading the metal before making a move. Once rotation begins, the plate advances while bending develops gradually across its length. Variable axis control defines the main action. Each roll shifts independently, allowing curves to form without flattening the edges. Pressure increases in controlled steps rather than a single push, keeping internal stress balanced. You'd expect steel this thick to fight back harder, but it follows along surprisingly well. The plate continues rotating, with curvature tightening as the rolls reposition on the fly. Refeeding and correction happen without removing the workpiece. The machine recalculates roll positions, refining the bend until target radius is reached. That mid-course adjustment always looks confident, like there's no second guessing involved. This approach reduces rework and keeps dimensional accuracy consistent across large diameters. Throughout the cycle, numerical control synchronizes motion, load, and rotation speed. Operators supervise parameters rather than wrestling with the material. Simple inputs, serious control, and no wasted movement anywhere in the bend. The result is a forming process built for heavy plates, flexible radii, and repeatable output across industrial applications. How controlled pressure on the Anyang 5,000-ton forging press reshapes heavy steel without fixed dies. Built for open die forging, the press shapes shafts, blocks, discs, rings, balls, plates, and complex forms by transferring energy through regulated pressure. Material handling sets the pace. Heated stock is positioned beneath the ram, while manipulators keep alignment stable. Load is applied in measured strokes, allowing metal to spread without locking into a fixed die. That steady push keeps deformation predictable. Pressure, speed, and travel adjust continuously as operators guide each reduction. Forging then moves through drawing, upsetting, and flattening. Repositioning replaces die swaps, keeping workpieces moving efficiently. You can feel how forgiving this setup is when shapes change mid-forging. Dimensional checks appear between passes, with hydraulic control compensating for resistance changes. The cycle ends with a refined form, ready for machining or heat treatment. Simple commands, serious force, no rush. Designed for heavy sections, the Anyang 5,000-ton press focuses on control, flexibility, and repeatable results across forging lines.
Steel sheets with remarkable consistency are crafted at Ilsenberger Grobleck GmbH. Each slab is inspected before entering the furnace to ensure chemical uniformity. Steel begins its journey in energy-efficient furnaces, where raw iron and alloying elements are melted into uniform molten metal. The molten steel is continuously monitored using thermal sensors for precise temperature control. Precise temperature control ensures consistent chemical composition and prevents structural defects. Automated ladle systems transport molten steel safely to the casting stations. The heavy rolling mills then transform these slabs into cordoblacier, gradually reducing thickness while maintaining flatness and strength. Operators adjust rolling pressure in real time to maintain structural integrity. It's fascinating to see how temperature control and rolling speed influence the final steel characteristics. After the primary rolling, sheets pass through precision levelers that correct any minor distortions, ensuring a perfectly flat surface. Levelers are calibrated daily to maintain tolerances within millimeters. Operators closely monitor sensor data to adjust rollers in real time for optimal results. Ilsenberger Groblech GmbH integrates heavy rolling, precision leveling, cutting, and surface treatment under one roof. This combined approach guarantees consistent quality for demanding sectors like construction, automotive, and energy. Surface treatments can include protective coatings for corrosion resistance. Finished panels are labeled and tracked to ensure full traceability. Staff members coordinate seamlessly with advanced machinery to maintain efficiency without compromising safety. Automated quality scanners verify surface smoothness and thickness. Observing the consistency and robustness of each steel sheet gives a real sense of manufacturing excellence. Smart cooling techniques control contraction and prevent warping. Energy-efficient furnaces and smart cooling techniques optimize material properties while reducing environmental impact. Waste heat recovery systems capture energy for other plant processes. It's surprising how subtle adjustments in processing parameters can dramatically change steel performance. Rolling schedules are optimized to balance production speed with material quality. Cutting stations then trim sheets to required dimensions, creating uniform panels for various industrial applications. The level of coordination between automated equipment and human supervision is impressive. Sheets are stacked according to size and specification to streamline logistics. Every cordoblac leaving Ilsenberger's facility is engineered to meet specific mechanical and dimensional requirements. The workflow exemplifies high standards of production and reliability. Continuous improvements in machinery, control systems, and handling protocols ensure the company remains a leader in heavy plate steel manufacturing. Energy monitoring systems track consumption to reduce operational costs. One can admire the blend of traditional metallurgy knowledge with modern industrial technology. Every stay ring is engineered to withstand extreme pressures within a hydroturbine. Metal composition is carefully selected to prevent fatigue under continuous operation. Each metal plate is measured and cut to exact specifications, ensuring the ring maintains structural integrity under extreme hydraulic pressures. The heavy fabrication units handle large components with precision, moving them through welding and forming stages. Watching these enormous pieces being aligned and secured is a testament to engineering skill. Machining centers refine the stay ring surfaces, smoothing and calibrating critical areas to maintain proper turbine alignment. Advanced CNC machines achieve tolerances down to fractions of a millimeter. Light metal precision machining tools polish the inner surfaces for exact fits, while heavy machining ensures that bolt holes and flange faces are within strict tolerances. Quality control teams continuously check measurements to confirm compliance with ISO 9001 standards. Dimensional inspections are repeated at multiple stages to ensure absolute accuracy. Assembly begins as components are brought together, with skilled technicians coordinating with overhead cranes and automated systems. Fixtures and jigs are used to maintain precise positioning during welding and assembly. Every weld is inspected to avoid structural weaknesses, and trial assemblies verify that all parts meet design parameters. Each stay ring undergoes hydraulic simulation testing to confirm operational reliability. From initial cutting and forming to thorough machining and assembly, EBCO Industries' process for the Francis Turbine stay ring blends robust engineering with high-precision techniques. Integrated production under one roof reduces handling errors and ensures efficiency. Every component is built for durability, efficiency, and long-term performance under extreme water pressures. The combination of heavy and light machining ensures both strength and precision in the final product. A thick steel plate rests under the immense 1,500-ton hydraulic press at the factory, perfectly aligned for edge flanging. You can't help but notice the sheer size of this machine. Slowly, the press descends, its hydraulic power compressing the steel with calculated force. Hydraulic pressure readings fluctuate slightly as the system balances the load across the plate. The metal shudders as pressure begins to form a precise flange around the edge. The flanging tool, mounted securely on the press ram, spins slightly to guide the plate into its final contour. Each rotation ensures the flange maintains uniform height and angle across the circumference. Operators monitor the pressure gauges closely, adjusting the hydraulic flow to accommodate variations in plate thickness. Once the first pass is complete, the press retracts, allowing technicians to inspect the flange's alignment. Technicians use visual markers along the plate edge to confirm exact dimensions. If needed, the plate rotates for a secondary pass, refining any slight inconsistencies. The press's control system logs every cycle for quality tracking. Even with plates several meters wide, the machine maintains consistent pressure across the surface. Next, the plate rotates slightly for the internal and external pressing operations. The die surfaces are periodically maintained to preserve accurate bend radii. The hydraulic pressure is applied uniformly across the contact surfaces, folding the edge without introducing roughness or wrinkles. Operators track press load readings to maintain safe and effective forming cycles. The angle of the die profile is designed to produce precise bend geometry. As the press continues its cycle, the die maintains a consistent radius, producing flanges that are both precise and repeatable. Final flange measurements are taken to verify conformance with design specifications. Cycle time optimization ensures productivity without sacrificing quality. After the flanging operation, the plate is inspected for uniformity and potential stress points. Technicians verify that the curves meet design specifications, checking that the bend angles and radii align across the entire perimeter. RPM Innovations applies laser deposition to compressor seals and complex geometries that are hard to repair traditionally. Metal powders are fed into the laser's focal point under strictly controlled atmospheric conditions. Laser deposition technology, LDT, allows these deposits to form strong metallurgical bonds, surpassing traditional mechanical joining methods. This method generates minimal stress and distortion compared to older repair techniques. The process can repair worn shafts, aerospace components, bearing housings, compressor seals, and custom freeform parts. Laser beam power and scanning speed are carefully calibrated to maintain consistent material properties. LDT encompasses direct metal deposition, DMD, laser metal deposition, laser additive manufacturing, LAM, and related methods. Rapid cooling rates lock in microstructural integrity for high-performance applications. Operators monitor powder feed, laser focus, and environmental parameters in real time. These measures ensure each layer fuses perfectly with the previous one. It's neat how layers accumulate to restore parts to precise dimensions. Various alloys can be used, including nickel, cobalt, iconal, titanium, stainless steels, 420, 316, 304, and hard-facing alloys. Adjusting laser paths allows repairs on complex geometries without dismantling entire assemblies. Quality control includes dimensional checks, surface inspections, and metallurgical testing. Every repaired or manufactured part meets stringent aerospace or industrial standards. Automation and operator coordination enable efficient, repeatable results. The low heat input protects surrounding material and prevents warping. It's almost like 3D printing metal with a scientific wand. Laser deposition technology at RPM Innovations demonstrates how modern additive manufacturing can repair, enhance, and create high-value metal components with speed, accuracy, and durability. The combination of rapid cooling, controlled deposition, and skilled operators ensures parts last longer than conventional repairs. From aerospace to industrial machinery, LDT delivers strong, reliable solutions. Massive crankshafts are forged and machined, each bearing journal inspected closely, passing through heavy-duty lathes and mills to ensure perfect alignment for engines. Engineering skill shines here. Steel bars are cut and forged into green pin shackles. Shackle eyes and pins shaped precisely, bodies bent, cooled, threaded, painted, and assembled in the Netherlands facility. Simple parts, but every step builds serious strength.
What turns flat tinplate into a rigid, sealed pipe without heavy casting or molding? This line shows how thin steel sheets are shaped, locked, and finished through controlled forming steps. Sheets are fed forward, aligned, and guided into rolling units that curve material into a round profile. Edge geometry matters here, as the seam must close cleanly without tearing. Formed edges meet and interlock while pressure stabilizes the pipe diameter. That joint looks simple, yet it decides everything downstream. The pipe advances through sizing rolls that correct roundness and length. Cutting station separates sections to specification, keeping each piece consistent for handling and stacking. Surface finishing follows to smooth contact areas and remove sharp transitions along the seam. You can almost feel how that makes assembly easier later. Calibration checks confirm wall shape and straightness before pipes move to final inspection. Seeing thin sheet hold its form like this feels oddly reassuring. Each step relies on steady motion rather than force, letting tinplate keep its coating intact. The result is lightweight piping suited for ventilation, ducting, and protective channels. Nothing rushed here, just steady control from start to finish. A simple bolt may look ordinary, but its accuracy depends on how precisely it is turned, and that's the focus at BKT during this CNC lathe demonstration. The sample bolt is produced to show how clear contour definition guides every movement of the cutting tool. This is one of those parts that quietly decides whether assemblies line up or fight back later. That moment when the tool approaches the material always feels tense, even though everything is calculated. Turning removes material step by step, shaping the diameter and shoulders according to the specified profile. As the bolt form develops, cutting parameters remain stable to maintain surface quality and dimensional accuracy. Clean contours here reduce the need for later corrections, which saves time across an entire batch. Grooves and transitions are cut in sequence, following the programmed geometry without unnecessary passes. After machining, the bolt is measured to verify that the contour matches the design. This demonstration highlights how simple contour descriptions translate into reliable CNC-turned components at BKT Duren. Uniform billet heating supports faster forging cycles using the InductoForge induction forging billet heater with tractor feed. Material enters the modular heating line in a steady sequence, guided forward without pauses. Induction coils surround each billet, raising temperature evenly through controlled electromagnetic energy rather than open flames. Heat builds fast while remaining balanced across the cross-section, preparing billets for downstream forging without surface damage. That consistency saves a lot of guessing later on. The tractor feed keeps spacing exact as billets advance, preventing overlap or cold zones between pieces. Power levels adjust along the line, matching billet size and production demand. As heated billets exit, temperature stability is checked before transfer to the press area. Seeing the billet glow evenly feels like the system did its homework. Modular sections allow the layout to scale or reconfigure as forging needs change, keeping uptime high across shifts. It's the kind of setup that makes long runs feel manageable. By relying on induction rather than combustion, energy use stays focused where it matters. The result is reliable billet heating that supports faster forging cycles while maintaining material integrity from entry to exit. Steel fabrication doesn't leave room for hesitation, especially when structures must align perfectly across tons of material at KMU Fabricator SDN, BHD, in Johor Bahru, Malaysia. This facility focuses on controlled accuracy and workflow clarity rather than speed, shaping beams and plates that are built to carry real loads. The workflow moves into CNC automatic beam drilling, where H-beams are positioned and drilled, using 3-axis drilling to achieve consistent hole alignment along the web and flanges. 3-axis drilling allows multiple faces of the beam to be processed in one setup, reducing repositioning errors. This step is handled by the CNC H-beam drilling machine, ensuring repeatable accuracy for structural connections. After drilling, beams and plates proceed to the CNC automatic cutting machine, which cuts steel members to specified lengths and profiles. The next stage uses a CNC automatic punching machine to create connection holes and slots, mainly for prefabricated plates. Cleanly punched holes simplify bolt installation during later assembly. When required, a manual punching machine supports custom or small batch adjustments. Prepared components then move into the welding stage, where plates and beams are joined into assemblies. Welding order matters here, helping control distortion across long structural members. Once welded, parts undergo finishing, removing surface irregularities and preparing them for surface treatment. Material handling systems transfer components to manual shop blasting, where surface cleaning is carried out for selected items. Surface preparation determines how well coatings adhere over years of exposure. Other components are routed through material handling for automatic shop blasting, feeding into the automatic shop blasting machine for uniform surface preparation. After blasting, parts receive primer painting to protect against corrosion. Hole covers are applied where necessary before moving on to second coat painting, followed by final coat painting to complete surface protection. Layered coatings extend service life in demanding industrial environments. Finished components are transferred to product stock, awaiting scheduling. Prior to shipment or site work, assemblies may be reviewed during pipe rack erection meetings. These reviews help confirm fit-up logic before components leave the factory. Supporting operations include vending machines, lathe machines, manual cutting machines, automatic marking machines, shearing machines, and manual drills. A 100 horsepower compressor supplies air for pneumatic tools throughout the shop. Consistent air supply keeps multiple fabrication stations operating without interruption. The process concludes with delivery, where completed fabricated steel components leave the facility for installation or further assembly. Power moves through a PTO shaft long before it ever meets a tractor. Manufacturing focuses on building a component able to transfer torque reliably from engine to implement. Steel tubes are cut to length, then formed to accept yokes that define alignment and load balance. Machining follows, shaping splines and bearing seats so rotation stays controlled under stress. That fit decides whether vibration stays quiet or turns into trouble. Yokes are assembled, cross kits added, and clearances checked to keep motion smooth during angle changes. Heat treatment strengthens critical zones, extending service life and demanding farm work. That toughness shows exactly why farmers trust it. Then coating protects surfaces from corrosion before final assembly. Each shaft is balanced and inspected to confirm it can handle real field conditions. Nothing here feels extra. Every step earns its place. The finished PTO shaft leaves ready to drive mowers, balers, and spreaders day after day. Operators and electric arc furnaces work side by side inside Sheffield's melt shop to control steel from the first heat. Everything that happens here sets limits the rest of the mill cannot escape. Electric arc furnaces load sorted scrap. Then energy is pushed in fast and direct, raising temperatures high enough to break metal back into a workable state. Operators track the melt closely, adjusting power and additions to keep chemistry within range. This control decides whether the steel can meet its intended use or not. Once the bath stabilizes, refining takes over. Slag is managed to pull out unwanted elements while alloying materials are introduced to shape strength and performance. These additions are timed to work with the melt, not fight against it. Ladles receive the steel and carry it forward, still glowing, still active. That heat isn't wasted time, it's a narrow window that has to be used right. At the ladle furnace, composition and temperature are corrected again, not rushed, not guessed. Each tweak has a reason, even if it looks subtle from the outside. From there, the steel moves toward casting. Continuous casting lines guide the liquid into solid form without stopping the flow. Cooling zones lock in structure, while rollers support the strand as it gains strength. This transition determines internal quality long before the steel is visible as a product. Alignment and temperature are constantly monitored to keep the strand centered and stable. Any deviation is handled immediately, because delays cost more than steel. Cutting stations divide the strand into usable lengths, preparing it for the next stage beyond the melt shop. This is where planning finally shows up in physical form. Every billet reflects decisions made minutes earlier, long before solid metal existed. Throughout the shop, teams stay coordinated, not by noise or speed, but by sequence and timing. By the time billets leave the line, the melt shop has already done its real work. Structure, chemistry, and reliability are locked in. What follows depends on this foundation, and there's no shortcut around it. Miss this stage, and nothing downstream stands a chance.
What allows a marine engine casting to handle extreme heat, pressure, and years of continuous operation without failure? At Hanshin Diesel and Kobe, casting is treated as a controlled balance between temperature, timing, and material behavior, refined through more than a century of engine manufacturing. The workflow prepares for pouring as molten iron is drawn from the furnace at 460 degrees Celsius, with a single ladle carrying 4 tons of metal. That heat isn't just about melting, it defines fluid behavior before contact with the mold. That kind of thermal control feels like holding raw power on a tight leash. The metal is guided forward without delay, keeping consistency intact before the next phase. Mold preparation shapes everything that follows. Sand is bonded using resin and hardener, forming structures that hold strength under extreme conditions. Cores are positioned inside the mold to define internal passages. Then, the mold halves are aligned with absolute care. That moment before closing the mold always looks like a quiet decision point. There's no room for hesitation. Pouring resumes at 343 degrees Celsius, with molten metal filling the cavity in just 58 seconds. Speed matters here, but so does restraint. The flow must remain steady, avoiding turbulence that could weaken the final structure. You'd never guess that 4 tons can move this calmly once everything is dialed in. At a later stage, another controlled pour follows at 363 degrees Celsius, reinforcing dimensional stability for demanding engine components. After cooling, excess material is removed and surfaces are refined during finishing. Risers and unwanted sections are cut away, leaving only the functional geometry behind. That clean separation always feels decisive, like the casting finally reveals its purpose. Inspection closes the loop. A high-performance 3D scanner captures the finished casting in detail, verifying dimensions and internal alignment against strict standards. This digital check ensures every component meets expectations before moving forward. From Kobe to global markets, Hanshin Diesel applies casting expertise built through marine engine production to support demanding industrial applications. Simple materials, serious responsibility, this is where heavy-duty reliability quietly takes form. Forming a bomb head flange without uneven stress is rare, and the BMB-25 flanging machine in Bursa is built for it, shaping bomb heads for industrial vessels with consistency that matters. This machine focuses on flanging accuracy while keeping deformation under tight control, a requirement when every millimeter affects final assembly. A formed head is positioned on the rotating table, where hydraulic clamps secure it firmly to avoid drift during operation. The flanging arm advances gradually, pressing along the edge, while synchronized rotation keeps the profile even across the entire circumference. That steady pressure feels like controlled power being applied one section at a time, and the result shows it. Operators adjust angle and feed rate to match material thickness, allowing carbon steel or alloy steel to respond without stress concentration. As the edge bends outward, the forming rollers maintain continuous contact, guiding the flange radius into specification. The hydraulic system delivers stable force throughout the cycle, preventing sudden loads that could distort the head. You don't expect such a compact press to handle this level of resistance so calmly, yet it does. The machine's structure absorbs reaction forces efficiently, keeping vibration low and alignment intact. During rotation, operators monitor edge geometry and make fine corrections directly at the control panel. This flexibility supports repeatability across batches, especially for pressure vessel components that demand uniform weld preparation. That flange grows cleaner with every pass, almost like the steel already knows where it's supposed to go. Once the target angle and width are reached, the head is released, ready for downstream welding or inspection. Built for heavy fabrication lines, the BMB-25 keeps output predictable while reducing manual correction. Simple mechanics, serious strength, and no wasted movement which explains why flanging remains one of its strongest roles in bomb head production. How does a bolted joint stay secure when vibration keeps attacking it during a Junker vibration test under DIN 65151? In the Junker vibration test conducted under DIN 65151, Nordlock washers are evaluated against other bolt securing methods to show how tension-based locking behaves under extreme conditions. The setup applies transverse movement to a bolted joint, repeatedly loading and unloading the fastener. Instead of relying on surface friction, the Nordlock system uses a wedge effect that maintains clamp load. That shift from friction to tension changes everything once vibration kicks in. As movement continues, competing locking methods lose preload rapidly, while the wedge locking washers hold resistance through each cycle. As the test progresses, loosening becomes measurable in real time. Load drops are tracked, showing how quickly a joint gives up stability. You'd expect any bolt to give in sooner or later, but this one refuses to back off. The washers react by converting movement into increased tension, keeping the bolt stretched and engaged. Repeated cycles simulate years of vibration within a controlled window. This method exposes weaknesses fast, without relying on long timelines. That steady pull feels less like luck and more like engineered stubbornness. By the end of the Junker vibration test, the difference is clear. Nordlock wedge-locking washers keep joints secure when vibration becomes constant and unforgiving over time worldwide use. Special steel bars at ASO Forge are built to handle loads that ordinary bars never face. They are shaped through coordinated heating, forging, and heat treatment, each step designed to control internal structure rather than rush output. This approach matters when bars are expected to perform under pressure, torque, and repeated stress. Billets are routed toward one of 4 reheating furnaces, where temperature is raised evenly to prepare the material for deformation. Instead of forcing speed, heat penetration is balanced to keep the core responsive during forming. That glow isn't about show, it's about making the steel willing to move without fighting back. Once ready, the billet advances to the 5,000-ton forging press, where controlled force compresses and elongates the steel into bar profiles. The press applies load progressively, shaping length and section while maintaining grain continuity. Operators coordinate press timing with transfer movements to keep deformation consistent along the bar. That downward force looks calm, but the tonnage is doing serious work underneath. After forging, bars cool under managed conditions before entering the heat treatment phase. Nine dedicated heat treatment furnaces handle normalization, quenching, or tempering depending on the required mechanical properties. Temperature cycles are selected to balance strength, toughness, and machinability for each order. You'd never guess how much planning hides behind a bar that looks this straightforward. Monitoring continues throughout, with adjustments made to furnace profiles to keep results repeatable across batches. Final bars exit with controlled dimensions and predictable internal behavior, ready for machining or direct use in heavy-duty applications. Simple shapes, heavy responsibility, and zero room for guesswork. From furnace to press to treatment, ASO Forge keeps the focus on steel that holds up long after it leaves the line. Engineers and automated systems move side by side at EMC Group, shaping how process automation supports modern manufacturing. The EMC 2015 Process Automation Revolution focuses on building an industrial platform where machines handle repetition while humans guide decisions across connected production lines. Machining operations rely heavily on automation, reaching roughly 80% coverage across the line. CNC units, transfer systems, and automated handling coordinate continuously to keep material flow consistent. That balance feels deliberate, like the line knows when to push and when to hold back. Instead of isolated machines, each station communicates status and output upstream, reducing delays before they show up as problems. Assembly follows a similar direction, with around 70% handled through automated lines. Components arrive aligned and sequenced, allowing robotic systems to complete fastening and fitting with stable repeatability. Human oversight remains present, stepping in where judgment matters most. This setup doesn't rush decisions, it just removes the waiting. By shifting labor away from repetitive motion, the system keeps attention focused on control and adjustment. One of the defining features is system-wide visualization. Quality data, machine status, and process conditions remain visible across the entire line. Deviations don't hide, they surface immediately. Seeing quality live like this changes how fast you react, almost before hesitation has a chance. Instead of post-process checks, feedback loops operate continuously. Service creation sits at the center of the platform. Automation isn't limited to production speed. It extends into how processes are designed, monitored, and adapted. It's interesting how the line feels less mechanical and more responsive the longer it runs. The structure allows changes to be implemented without dismantling existing workflows. EMC Group positions this approach as an international automation solution platform, connecting machining, assembly, and service through shared control logic. Once everything is visible and connected, the whole operation feels harder to disrupt than you'd expect. The result is a production environment built for consistency, adaptability, and long-term stability. The workpiece spans a wide area, yet the TRIMILLVM 6545 keeps milling paths controlled. This portal machining center handles oversized workpieces by keeping stability front and center, turning raw blocks into accurately milled components without rushing the cut. Capacity matters here, but consistency matters more. A heavy workpiece is fixed on the table, aligned to stay steady through long machining cycles. The gantry structure supports the spindle as it travels across wide surfaces, removing material layer by layer. That cutter engagement looks confident, like the machine knows it won't flinch halfway through. Feed rates and tool paths are adjusted to balance surface quality with material removal, especially on large flat areas. As milling progresses, the VM 6545 maintains even pressure across the entire stroke, reducing uneven wear on tools. Operators monitor the run and refine parameters directly from the control system to keep dimensions on target. You wouldn't expect such a wide travel to stay this composed, yet the motion stays controlled. Chips build quickly around the table, a quiet sign of steady productivity. This setup feels like strength stretched over distance, not squeezed into speed. Once machining completes, the part leaves the table ready for finishing or assembly. $360,000 tons of steel move through MedSteel's production lines each year in the Kurdistan region. Melting, billet casting, and bar rolling run as one integrated system. That scale feels steady rather than rushed. Powered by a 52 megawatts plant, output stays consistent while keeping long-term sustainability in focus. Tower sections only stand strong if every seam holds, and Katana Summit proves that in Columbus, Nebraska. Steel cans for wind towers are rolled, aligned, and welded into long tubes that carry the load above ground. Lincoln Electric welding systems deliver stable arcs across extended joints, while operators guide each pass along the circumference. That seam stretches farther than you expect, like strength being stitched in one line. Heat input stays controlled to limit distortion.
A kitchen knife earns trust long before it reaches a cutting board, and that trust is forged into every blade at Zwilling J.A. Henkel's in Solingen, Germany. Here, knife forging is built around durability and balance rather than speed, reflecting standards that have guided production. The long history isn't decorative, it shapes how every decision on the shop floor is made today. The focus stays on how steel behaves under force, not on shortcuts. Steel blanks are heated to reach a workable state, allowing the material to respond evenly when pressure is applied. They move into forging dies that shape the blade profile while compressing the internal structure for strength. This compression improves grain alignment, which directly affects edge stability over time. That press stroke looks calm, but the steel clearly gets the message. Forging also establishes the tang and spine thickness, setting the foundation for long-term stability. After forging, blades pass through controlled cooling and heat treatment to harden the steel without making it brittle. Tempering follows to balance hardness with toughness, ensuring the blade can handle daily use. Hardness targets are chosen so the edge resists rolling without becoming fragile. You'd never guess how many decisions sit behind a blade that feels this steady in hand. Each stage influences how the edge will behave later. Grinding refines the blade geometry, thinning the edge while keeping symmetry intact. Automated systems handle consistency, while skilled operators guide adjustments where needed. Small changes in grinding angles here affect how smoothly the knife moves through food later. That edge line sharpens up fast, almost like the steel knows its role already. Surface finishing smooths the blade and prepares it for final sharpening. Handles are fitted and secured to align with the forged tang, keeping weight distribution comfortable during use. Assembly focuses on balance as much as attachment, so the knife feels natural rather than heavy. This is the kind of balance you notice before you even start cutting. Final inspection checks dimensions, hardness, and finish, confirming each knife meets strict criteria. From forging to finishing, Zwilling J.A. Henkels maintains a process that values consistency across generations. Simple movements, serious expectations, and zero tolerance for guesswork. That's how a forged kitchen knife leaves Solingen ready for years of work. From stamping lines to final road testing, YUTONG Superbus manufacturing runs as one system. The work stretches across spare parts processing, body and white assembly, painting, chassis assembly, and interior and exterior installation, spanning more than 100 workstations. Stamping and rolling lines form body panels, doors, front and rear walls, and compartment structures. Roller machines reshape sidewalls and roof panels to meet strength and appearance targets, while squeezing and cutting units bend high-strength steel into semi-finished frames for different bus models. This is where flexibility really pays off. Automatic welding replaces manual work, joining front, rear, side, roof, and floor frameworks into the Monaco Q structure with consistent results. Aircraft manufacturing concepts guide weight reduction and space use, improving load balance without sacrificing durability. Annular frame members reinforce impact resistance, pushing body strength further. That structural logic feels closer to aerospace than road transport. Painting relies on RFID for automatic transfer between stages. Bus bodies, up to 14 meters long, pass through 15 treatment pools, then curing and cooling. Salt spray resistance exceeds 1,000 hours, delivering long-term corrosion protection. Multi-purpose robots and pigging technology allow rapid color changes. Color switches happen faster than expected. Chassis and power systems follow, using second-generation thermal management to hold coolant near 90 degrees Celsius, reducing energy loss. Final assembly brings together over 20,000 components on 21 stations within 2 days. After shower tests, simulated rainstorms, inspections, and a 30-kilometer road test, performance checks close the loop. Seeing everything come together feels unexpectedly calm.